Okay, so we're recording. We're discussing the beginning of page 4 of the section 5.2 notes. And here's example 2. If Mr. Reyes, who's our assistant principal academics, drives continuously 130 miles in 2 hours in his Ferrari starting from rest, will there necessarily be at least one instance when his speedometer will be 65 miles per hour and 40 miles per hour? Now I'm going to tell you right now the answer for both these is true or yes. Yes and yes. The answer for both these are yes and yes. Now let me give you the reasons why. I'm going to use a text box here. The first reason is because of it, and I'll only type it out first, is because of MVT, since the average rate of change is 65 miles per hour, where you do 130 minus 0, then there will be at least one instance when the instantaneous rate. And let me finish typing. I'll let you guys copy it. Okay, here we go. So I'll read it again. Because of the mean value theorem, that's the reason why. Since the average rate of change is 65 miles per hour, because you're going from 0 to 130, 0 to 130 miles in 2 hours. So you simply just divide the change in distance or change in time. There will be at least one instance when the instantaneous speed equals average rate of change. That's just part of mean value theorem. The second one is true also. Does anyone remember what theorem that would be? What theorem we would use to help us understand part B?
Is it IVT?
Oh, good. Who said that?
Me, Arush.
Oh, thank you, Arush. Yeah, perfect. Thank you. Yes, it's IVT. Exactly 100% correct. And so let me kind of give you the explanation. So it's because of IVT. And since the lowest speed is 0 miles per hour, high speed could be 65 miles per hour, then we are guaranteed all values in our interval. Okay, let me size that just a little bit. Okay, here we go. So because of the intermediate value theorem, since the lowest speed is 0, because you start from rest, right? They said that. You know, how do I know lowest speed 0? How do I know that? From rest. You're not traveling. That's 0 miles per hour. What's the high speed I would achieve? I know at least we'll hit 65 miles per hour because that's our average rate of change. Do we go faster than 65 miles? Maybe, I don't know, but I know at the very least, we definitely hit 65 miles per hour at least once. So IVT states that you'll be able to take on any value between your lowest and highest y value. So let's say speed is y and time is x. So whatever interval you're looking at, maybe from 0 to, actually from 0 to 2 hours, obviously. Any y value in between 0 and 65 can be taken on. Now the assumption here is continuity, and here continuity and differentiability. So you have to assume those. And we would. I mean, if you're driving a car, it's not like, you know, if you're looking at your position. So if this is position, this is time. Same thing with velocity too. It's not like all of a sudden, like here's your position and oops, all of a sudden you kind of just quantum leap and you're here now. Well, likewise with velocity, if you graph your velocity with time, you know, you're going like 0 to 40 miles per hour, and all of a sudden you go from 40 to 80 without passing all the numbers between 40 and 80. That makes no sense. You can't do that. So that just doesn't work that way. So that's what's going on there. Okay. Now let's look at corollaries. Corollaries are extensions of theorems, which you might remember from geometry a while ago. So the first corollary, given a function is continuous on there from A to B and differential, so you're using all the assumptions of mean value theorem. If your derivative is positive for each point in this interval, then you can say f is increasing on the interval. If your derivative is negative, then you can say f is decreasing on the interval. And I'm going to look at some examples just a little bit so you guys can see this in action. You are told to pay careful attention to the parentheses and brackets. That can be a little confusing. Just, you know, I'm not going to be too bent on intervals so much. I mean, there'll be times when I do care, and I'll tell you when I do care. This is one of the instances when I don't care too much, because actually it's kind of debatable when you're saying something's increasing and decreasing to include the x coordinate where you end the interval, or to not include it. It's so sometimes in the College Board they'll just say just give me the open interval, just to avoid that kind of ambiguity. So in this case, I don't care too much about whether you do an open or closed interval when you're talking about what's increasing or decreasing. But the thing that is important is that you have to make sure your derivative is positive if you're increasing, if you're going to include it. If your derivative equals 0, then of course you're not positive. So you just have to be a little bit mindful about that. But looking over here, given f is a function defined on an interval I, x1 and x2 are points on I. So say, for example, I call this x1, and say I call this x2. Clearly the y value at x2 is bigger than the y value at x1. So when this happens, we say that we're increasing. When your y value at x2 is bigger than your y value at x1, assuming x2 is bigger than x1. So if you plug in a bigger number and the y value is also bigger, so essentially as x increases, y increases. That's what's meant by increasing. So they're both increasing at the same time. Likewise, they could also both decrease at the same time if you're going, from right to left. But imagine if you're going from left to right, what's happened to y? It keeps going up. Now, here's the other way around. What if you have this? So let me kind of draw it a little differently here. Here's x1. Here's x2. So clearly x1 is less than x2 here. And the y value at x1 is bigger than the y value at x2. We call that a decreasing function. So what's happening here is that the y values are dropping. So as x increases, y decreases. And we call that a decreasing function. Now, some other things to keep in mind. If you look at the box where I just wrote stuff on top of it, that wasn't too smart, but this is another kind of important thing to look at too. Assuming your function is continuous at some interval from a to b or from b to c. And let me actually go back here and call this like, say x. So clearly x is in an interval from a to b. If you drew a tangent line here, is your tangent line positive or negative? Well, it's obviously positive here. When that happens, then your derivative is positive. Therefore, you're going to be increasing, assuming that everything stays positive. I mean, all the tangent lines are positive between a and b. Then it's increasing. Whereas over here, oh, sorry, I'm yawning a lot. Probably need to get some coffee or tea here. Yeah, it's very exciting stuff, right? Trust me, that does get more stimulating. Just wait. You're between B and C, right? X is between B and C. Now notice my tangent line's negative here. So my derivative is negative. When that happens, if all the tangent lines are negative between B and C, then we say it's decreasing. So you really want to pay careful attention to the slope of the tangent lines. If your slope of the tangent line is positive for the entire interval, it's increasing. If your slope of tangent lines are negative for entire interval, it's going to be decreasing. And this will play a very key role in what we do on Thursday and some of the applications we do with this, which unfortunately we don't get to until post-session. I just couldn't squeeze it in because then I'd be neglecting some other more important topics. And we have very limited time here. So anyway, for example 3, this will be very mechanical, like was example 4, and then we'll move on to some more corollaries. You're asked to determine the intervals where this function is increasing and decreasing. So the first thing you're going to want to do is work out your derivative. I'll do it off to the side here. What's my derivative here? 3x squared minus 3, right? That's easy. Now, you're going to set it equal to 0 and solve for x. Okay, so x is plus or minus 1. Now what you're going to do is you're going to do a sign chart. You guys remember sign charts from back in the day? And remember, we call these critical points here because it's what makes the derivative 0. You also do want to look for what could make the derivative undefined as well, or does not exist. So we are looking for critical points. Then what you do is you plug in values within each interval into the derivative. So so you plug these. So here we're looking for a sign of f prime, and these are all x values down here. For example, 2. Let's plug 2 into the derivative here. If I plug in 2 in this derivative, I get 3 times 4 minus 3. So the answer is 9. So that's positive. If I plug 0, I get negative 3. So it's negative here. If I put in negative 2, it's also going to be positive. So what you're doing is you're creating these intervals, and you're deliberately picking x values within each interval and throwing it back into the derivative, and checking to see if the derivative is positive or negative. Clearly my derivative is positive when x is bigger than 1. Clearly my derivative is negative when x is between negative 1 and 1. Clearly my derivative is positive when x is less than negative 1. So here's what we're going to say about increasing, decreasing. And this is actually the right way you want to type it too. So I'll do a little text box again. So let's see here. So f of x is increasing on, you're going to say, negative infinity to negative 1 because f prime is positive. Actually, hold on a sec, there's more. Almost done typing, give me 1 sec here. Okay, so I just typed part A. Here's what you would say: fx is increasing on, and you have to give the interval from negative to negative 1, union 1 to infinity, because f prime is positive on the intervals from negative to negative 1, and union to 1 to infinity. So this is what we call AP style language. Okay, it's called AP style language. You have to be formal with the way you write this. I will not accept sloppy work here. And what I might do is, maybe when I look at your homework, I'll probably scrutinize it a little more closely. It may just give some feedback, and I won't take out points, but I'll just say, hey, make sure you're taking work a little more seriously, because the College Board does care about that. So that's what you would say. Yeah, of course, f prime is positive on those intervals. We included negative 1 and 1. If you don't worry about it. I guess you're increasing up to negative 1 and up to 1. It's kind of weird. That's why I don't worry so much about the closed bracket on negative 1. If you put open, parentheses for negative 1 and 1, that's I won't penalize you for that. The infinity, you can't put brackets though, because infinity, we don't know what that is. Like, remember, you put brackets because you're including stuff. I don't know what the number infinity is. That's part A. And for part B, just gonna do a little copy and paste, change colors. So you can see now it's decreasing from negative 1 to 1. Because it's negative. Okay. And that's how that one works. So again, clearly we're negative on that interval. So now why don't you guys try, I guess I'll do this one with you guys, but then I'll maybe have you guys figure out how to write it, and then we'll keep moving forward. Okay. So same thing here, but now we have a more challenging, well, it's not too challenging, but just a little more challenging derivative to do. That's going to be x times 9 minus x raised to the 1/2 power. So you got to do a product rule. So 1 times 9 minus x to the 1/2 plus x times 1/2 times 9 minus x raised to negative 1/2. and times -1, by the way. You got to do a chain rule, right? The inside is 9 minus x, so times -1. So in this case, you're going to have root 9 minus x. It'll be minus x over 2 root 9 minus x. I believe I've done that correctly so far. Yep. And yeah, you can put 0 over here. Move everything over to one side. Not everything, sorry, just one of those things over to one side. Cross multiply. You multiply radical by radical, they knock each other out. So x equals 6. So that's your critical point. We don't have any endpoints here, don't worry, but you can't do anything less than 9. Anything greater than 9 because it would be undefined, free radical. So we'll stop at 9 there. Question in the chat. Wait, why did I multiply the second part of the product rule? Because it's chain rule. That's why. Good question. Always asked. It's because of chain rule. So remember, when you had 9, let me actually highlight in red so you guys can see a little bit better. I probably should change colors so it's easy for you guys to see. So you got this, right? When you take the derivative of that, remember the 1/2 goes to the front. Still got the x that's intact over here. You drop the exponent by 1, you keep this intact, and the derivative, what's the derivative of 9 minus x? It's -1. That's why you have to do that. It's part of the chain rule. So like, for example, what if I had x squared plus 1 raised to the 1/2 power? What's that derivative? We'll put the 1/2 to the front, drop the exponent by 1, and then multiply by the inside. That's the reason why. The derivative of 9 minus x is -1, because derivative of 9 is 0, derivative of x is -1. So hopefully that makes sense. Okay, now why do I have 9 in the sign chart? Good question. Fantastic questions, guys. You guys are, and again, there might be a little rust too. So definitely ask, because I am kind of assuming. I did do a little bit of stuff with the. I kind of didn't do the best job with the AP study groups last month. We did a little bit of review, so hopefully, and I did put some product rule, chain rule stuff, and I know not everyone participated in them, which is totally fine too. But anyway, why I'm putting a 9 here? Because you can't go more than 9. If you plug in 10, you have an imaginary root, right? If you plug in 10, you have root -1. That's a problem. So I'm not going to look at anything. And by the way, this is x, and this is the derivative of f. I'm not going to look at anything over here. I'm only going to look at values between 6 and 9 and less than 6, like say 8, for example, or 5, for example. Well, if I plug in 8, I have 8 times √1. That's positive. If I plug in 5, actually, hold on a sec here. Oh, wait, did I make a mistake? Oh, I'm an idiot. Sorry, guys. You have to plug into your derivative, not the original function. My apologies. Okay, if I plug 8 into the derivative, my apologies. That's √1. Yeah, remember, you got to plug in to the derivative to see what the sign of it. So that's going to be √1 minus 8 over 2 √1. That's going to be a negative number because you have 1 minus 4. So it's, my derivative is negative here, anything between 6 and 9. If I plug 5 into here, into my derivative, you have √4 minus 5 over 2 √2. So it's 2 minus 5/4. So that's going to be positive. So I have a positive here. So clearly, I'm increasing this interval and decreasing that interval. And then you could just say from -infinity to 6, you're increasing. You're decreasing between 6 and 9. And you can't include the 9 actually because it would make the derivative undefined. So we don't actually include it. But honestly, I'll probably just multiple choice problem, and I'll just put the choices out there, and I'll just, I'm not going to trick you with the whole parentheses bracket stuff. But what I do care about is that you know how to find the derivative, you know how to find the critical points, and you know how to test it into a sign chart. That's what I care about. And this will help with actually figuring out how this graph will look, because the graph will be rising up to 6 and then dropping from 6 to 9. Let's keep moving here. Now, what if your derivative is 0? What kind of functions do you have now? So what sort of function has this happening for all values of x? Constant functions. So like, say for example, f of x equals just 4. Well, the derivative is just 0, regardless of what you plug in for x. So that's something else just to keep in mind. And actually, that's the next corollary. If your derivative equals 0, then your function is a constant, and we call it capital C. Or if f prime of x equals 0 at each point in the interval, then there's a constant C for which f of x equals C for all values of x in that interval. That's hopefully should seem intuitive. The next one should hopefully seem intuitive as well. We'll do a little proof with it, and then we'll start talking about antiderivatives, and we'll be coming up on a break very soon. Okay. And you guys, again, asking great questions, guys, staying super focused. That's awesome. So let's say f prime of x equals g prime of x. Okay, great. So you have two derivatives are equivalent to each other. Then what this means is that f of x will equal g of x, but plus c for some constant in that interval. So why does this make sense? Like, how do we know this? Well, what if I take the derivative both sides right now? So h prime of x equals f prime of x minus g prime of x. Okay. Now, because this is true, since f prime of x equals g prime of x, then f prime of x minus g prime of x has to equal 0. Therefore, h prime of x equals 0. So hopefully that makes sense there, because again, if I take the derivative of both sides, you get this. And because I made this statement early on, f prime of x equals g prime of x, if I move g prime of x from right to left, I have f prime minus g prime, that's 0. So h prime of x equals 0. Then h of x has to equal a constant as part of the second corollary. Or we'll call it C, capital C for constant. So capital C now equals f of x minus g of x. Therefore, f of x equals g of x plus c. This is all under the assumption that you start off with f prime of x equals g prime of x. So if you start with that assumption, f prime of x equals g prime of x, we can safely conclude that f of x equals g of x plus c because of this proof we just did. And that's going to be kind of a big deal because it's going to enable us to do antiderivatives in just a second, which we're going to get to in the next few examples before we wrap up these notes. Okay. So let's look at example 5. Find all possible functions with a given derivative f prime of x equals 7. Well, we could say is that f of x equals 7x, or you can say f of x equals 7x plus 2, or you could say f of x equals 7x plus any constant. Because if I take the derivative of 7x, I get 7. If I take the derivative of 7x plus 2, it's 7. If I take the derivative of 7x plus any constant, it's still 7. So they only differ by a constant. Let me change that to a different color here. So to find all possible functions where the given derivative is f prime of x equals 7, you only really need to find just one such function, because all others just differ by a constant. So how do you write this? How do we write this? You write as f of x equals 7x plus c. And that's considered the family of solutions. We tend to call that, we call this a family of solutions, because there's a whole bunch of functions that would follow that. 7x plus 1, 7x minus 2, 7x plus 3.56, 7x plus a billion. Just a general way of expressing your answer. And so this will lead us to a bunch of pretty simple problems that we'll do up to the end of page 7. Then we'll do a linear motion problem, then we'll take a break. Okay, so let's take a look down below. Find all possible functions of the given derivatives. Well, if you think about it, f of x will have to equal x to the 4 power over 4. How do I know that? Well, what's the derivative of x4 over 4? It's going to be 4x cubed divided by the 4 there, and those 4's cancel. I will teach you guys techniques of how to do this more effectively, but I'll kind of just tell you right now that if you do see a linear, sorry, not linear, a power term like a monomial, like x to the n power, if you do an antiderivative of that, you just add 1 to the exponent and divide by a new exponent. That's really what you do. I'm going to talk about these techniques next week anyway. But really, how do I write my answer here? And by the way, this is all being recorded, just so you know. You watch stuff over again, because I know I'm giving you guys a lot of information here. But really, you got to write like this, plus c. Because if I take the derivative of this, what's that prime of x going to equal now? 4x cubed over 4 plus 0, because the derivative constant is 0. You just get x cubed. Here, what's the antiderivative? And you can actually use this in case you guys forgot. Yeah, the derivative of cotangent is negative cosecant squared x, so you kind of just go the other direction. So in this case, you'll say negative cotangent x plus c. Because the derivative of cotangent is negative cosecant, and then the two negatives cancel each other out. And the derivative constant is 0 anyway. Again, why do I have a negative? Because the derivative of cotangent is negative cosecant squared. So you have the extra negative attached to the cotangent, so that cancels out, getting you back to cosecant squared x. Let's look at c here. This right here, you'll see why we have it in just a second. but it's 1 over something. So f of x will equal natural log of the absolute value of x minus 3 plus c. So if you put that, then you don't, I suppose you don't really need this part right here. But I guess because you have it here, you probably don't need the absolute value. I mean, I guess if you wrote this, you've been fine, because you already assumed that x is greater than 3, so you're not going to be logging any negative numbers. But I like just to be on the safe side, just put absolute value anyway. When you have 1 over something, like 1 over a linear term, and you're doing the derivative of it. And again, plus c. So this entire process that we're doing is called anti-differentiation. Let me actually type that up. It's called anti-differentiation. That's what this process is called, anti-differentiation. So for example, 1/4 x to the 4, 1/4 x4 plus 2, 1/4 x4 minus 3. Those are all anti-derivatives of x cubed. Because if I took a derivative of those, I would get x cubed. So the antiderivative is the opposite of doing the derivative. Or you could think of it this way. If f of x equals, say, x squared plus 1, then f prime of x equals 2x. Therefore, x squared plus 1 is an anti-derivative of 2x. So it's just reversing what we've been doing all along, or all stuff we did in the fall. We'll see with example 7 now. Here he has to find a function, f of x, that has the following derivative and actually passes through that point. So now that you're told that a point passes through, what you want to do, you use this to find c, the plus c or the constant. So let me do this up above because I'm running a little short in space here. We'll change colors for a bit of contrast. So let's do example 7 up here. Obviously, you have the space in your notes if you printed these. So f of x, it's a little tricky. Anyone have an idea of what f of x is going to be? Like what kind of function or exponent we're going to see? Remember, it's like saying 1/3 times x to the negative 2/3. That's my derivative. So where did it come from then? What was the original function? X what power?
1/3.
Yep, 1/3. Good. Because the derivative of that, you move the 1/3 to the front and drop the exponent by 1. Plus, I already kind of explained to you the mechanical process, which again we'll talk more about next week. If you add 1 to the exponent, and then whatever the new exponent is, divide by that number, that would be your antiderivative. And that's, we would get x to 1/3 if you did that. If you added 1 to negative 2/3, negative 2/3 plus 1 is 1/3. Divide by 1/3, the 1/3 already there and the 1/3 down below are going to cross off. And of course, plus c. Now, if I use my initial condition, I'll plug in -1 for f of x and 8 for x. Remember, f of x is like y, right? Then -1 equals 2 plus c, c equals -3. So the equation is going to be f of x, or the antiderivative is going to be f of x equals x to 1/3 minus 3. So Okay, then we'll try one more because we're just so close to getting these notes complete, and then we'll do a break. Question in the chat. Can you explain how you got x to the 1/3? Yeah, of course. Let me go and clear my screen here because it's getting a little busy. So it helps if you rewrite this. That's 1/3 times x at -2/3. That's f prime of x, right? So what you could do is this. Add 1 to the exponents and divide by your new exponent. Well, when I add 1 to the exponent, the new exponent becomes 1/3. So you divide by 1/3. These cancel, and that's to get x to the 1/3. Because remember, -2/3 plus 1. And just there's a lot of fraction stuff we do. So if you're feeling a little iffy on fractions, that's okay. Feel free to use a calculator, or just remember whole numbers can be treated like this, and you make it 3/3. So that's why I get x to the 1/3. So that's the technique you would do, is that you'd add 1 to the exponent and divide by the new exponent. When adding 1 to -2/3, I got 1/3, so I divide both sides by 1/3, and these 1/3s cancel. Or if you just think about it, you could think about by intuition somewhat, is that if y equals x to 1/3, what's y prime going to be? 1/3 to the front, drop the exponent by 1. That's a derivative. Antiderivative is the opposite. You add 1 to the exponent, divide by the exponent. Instead of subtracting by the exponent and multiplying, or you move the exponent to the front, then subtract by 1, you do the opposite. Okay, let's talk about one more here. Let's look at example 8. So example 8, and then we'll do a break. I promise I'll give you a 10-minute break because I need one too. Find the velocity position functions if your acceleration happens to be just 12 straight up. So your acceleration is just 12. So the velocity is 2 seconds. Sorry, if your velocity at t equals 2 is 4 meters per second, and your position is -11 meters also at 2 seconds. It's 11 meters from the origin. Got it. Okay. So here's the deal. A of t equals 12. So the antiderivative, so since v prime of t equals it, you got to remember that the derivative velocity is acceleration. Then antiderivative of acceleration is v of t. So v of t is going to be 12t. Because what's the derivative of 12t with respect to t? Just 12. And plus c. Now you have an initial condition here. When t equals 2, the velocity is 4. So c is -20. Plus, here's how you can check. What's the derivative of 12t minus 20? 12. So that's your velocity function. Now, since position, which I'll call s prime of t equals v of t, we know this, then the antiderivative of v of t is s of t. So what I'll need to do here, and that's a 20 by the way, sorry. I'll need a little space. We'll do it over here. The antiderivative of 12t minus 20 is going to be 12t squared over 2. Remember, you add 1 to the exponent. Right now, exponent's 1. Add 1, divide by the new exponent. Minus 20t, because the derivative of -20t is going to be -20. And plus, you don't see a variable here, so you just kind of tack it on. And then plus c. You could imagine that there is a t there, and it's t to the 0 power, if that helps. Because anything to 0 power is 1. If you add 1 to this and divide by 1, you get negative 20t. So that's going to be your s of t function. But you have s of 0. Sorry. I meant to say s of, is s of 2 or s of 0? I guess it is. Oh, it is. Okay. Well, that's kind of weird. It's initial position. Got it. I didn't read that carefully. It's initial position. So that's s. So that's t equals 0. I thought it was the same time. It's t equals 0 is negative 11. Got it. So negative 11 equals 6t, because that's 6t squared, right? So you could do 0 for t, 0 for t. C is negative 11. So s of t will equal 6t squared minus 20t minus 11. So that's doing an antiderivative. And you'll have a chance to practice in the textbook problems. You'll have a chance to practice, and we'll talk more about it on Thursday for sure too. Okay. So we covered quite a bit of stuff. So let's take a 10-minute break. It's 2:20 right now. 2:30. Well, on the West Coast, I don't know if some people. I have one student who's actually. Well, I'm not sure in this class, but someone had emailed me there in Hawaii in the other class, the 8th period, and some people might be in the East Coast. I don't know, but anyway, in 10 minutes, let's come back. We'll do some practice problems from the worksheet using MVT because you guys need a little more practice of that. And then you'll have the textbook problems, which will talk about increasing, decreasing intervals, and of course, this antiderivative stuff, especially with linear motion. And I'll stop the video because this ends the video here for that. So let's come back in 10 minutes, okay? And I'll just turn off my mic and video as well.